Good morning. This is mini lecture A from summer B of 2017. We're going to talk about the relationship of electron standing waves in atoms and the structure of the periodic table. And along the way, we'll talk about guitars. The key idea for understanding all of that is the containment of the electron in its Coulomb interaction with the positively charged nucleus. And here's a picture of the spectrum of helium. Looks different from hydrogen's spectrum. And we're actually going to talk about helium and all the rest of the periodic table in this mini lecture. Let's start with a mini review of standing wave concepts, and we'll compare standing waves to free particle waves. And I'll give you a reminder about the YouTubes that are available to you about that. Now, Louis de Broglie made his famous conjecture about electrons and atoms, and we have talked about that and studied that already this summer. Basically, if an electron is like a particle of light, a photon, then it ought to have a wave property. And he said, if you then apply that to an atom that keeps an electron in a bound orbit around the positive nucleus, the electron in its circular path around the nucleus would have a particular wavelength, and it would fit into the circumference of the orbit. Now, I compared that to the standing waves in the YouTube videos from the lecture hall that we have done in semesters past. So my old TAs, Amanda and Riley, they're in YouTube. Caroline and Darian, my TAs from spring 2017, they're in YouTube. And the important thing is that once the two TAs set their feet on the ground, they stand there and they wiggle the coil spring up and down, and then they don't move until they want to do another demonstration. But once they fix their feet, only certain frequencies of oscillating that coil spring will result in a standing wave. So until they get the right frequency, they won't achieve a fundamental. And then they have to change the frequency again, but the coil spring is all discombobulated and disorganized, chaotic, until they hit the right frequency of wiggling it, and then they get the first excited state, which is a bump and a dip oscillating with a dip and a bump. And you can look at it in YouTube and see it. Then if they increase their frequency, decrease the wavelength, just to the right frequency, they can get the second excited state, which is a bump, a dip, and a bump, oscillating with a dip, a bump, and another dip. Right? And you can see those on YouTube. Sometimes you can see the third excited state, which is kind of tricky, but you can do that. So I invite you to all look at those demonstration videos in YouTube again, just to understand that not every frequency and wavelength will achieve a standing wave. Once you have set your feet, once you are contained, once that coil spring is contained, and it's the same with electrons on the orbit around the nucleus. All right, now here's a picture from page 237 of the e-textbook, figure 9.8. And yeah, this one has just the right wavelength. All right, electrons don't really look like this, but it's a good enough conceptual diagram that we can use it for the basic ideas. And this one has 4 full wiggles, 4 full oscillations of the wave for 1 full lap around the nucleus. Now, that's the perfect wavelength, or one of the perfect wavelengths. There's other perfect wavelengths for 6 full oscillations per lap, so on and so forth. But any other wavelength might be a no-go. Any other frequency, nope. You're not going to necessarily get a standing wave, right? And that's what this picture shows you. Now let's review what the wavelength is related to. We know this. We've talked about it already. It's related to the momentum. Now here's a formula: mv momentum equals h over lambda. That's kind of the flip-flop of the de Broglie relation that we have been using the past week or so. But it's considered kosher, and I'm emphasizing in this the momentum state. H controls which momentum states are allowed in the atom through this equation. So Planck's constant controls the whole shooting match. And because it controls the momentum state, it also controls the energy states. And only certain momentum states, only certain wavelengths, only certain frequencies, and therefore only certain energy states are allowed. And those, that countable set of energy states and wavelengths, frequencies, and momentum, that is quantization. That is how an electron becomes a quantum system. Uh, and so when we look at the spectrum of hydrogen, we have a countable set of colors, a countable set of energy levels, and it's because of this containment idea that's occurring with the standing waves of electron. Now, the key distinction is that quantization occurs with containment. You've got to have some kind of containment. And you can see that on the YouTube in the classroom. The containment method there is just the two TAs standing in one place and then trying to shake the coil spring at the right frequency. Right? In the atom, it's the Coulomb interaction. And there's other ways to achieve quantization and stuff. But in atoms, it's the Coulomb interaction in all of its various variations. Now, the other thing is that without containment, for instance, a free particle, a free electron, you can have any energy and momentum state theoretically. If you can accelerate it to 88 miles an hour or to 99.9% of the speed of light, the electron's perfectly happy to do that, unless it's confined. And if it's confined by the Coulomb interaction in an atom, nope, you only have certain wavelengths, frequencies, momenta, and energies. Now, let's relate this idea of standing waves to music, because music can be really helpful for understanding a lot of things in this world. And without music, the dance is over, unless you know somebody that can play the guitar. And so, let's take a look at the whole idea of a chord on a guitar. Okay. Every chord requires particular strings, and that's the whole skill of playing a guitar. You know which, and each of those strings has a required specific length. Right now, you might not put your fingers on each of the strings, but some of them, yes. So you touch the string at the left end points, or you let the nut at the end of the fretboard be the touch point. Okay, and so either your fingertips or the nut at the end of the fretboard control the length of the strings. Okay, you control it. So there's your containment. You control the length of the strings. Therefore, you control the wavelength of each string's fundamental mode and all the other harmonics. You control them by putting your fingers or using the nut to control the length of the string. Therefore, you control the wavelength, you control the frequency. The frequency is the pitch. So what you're doing, when you control the length of the string, you're controlling the pitch of the sound that each string puts together, or that each string produces. And then you strum your chord. And that is where you win the victory, because my wonderful students, sweet music, that is the entire reason that guitars exist. So, let's use that idea of chords, standing waves of electrons, to think beyond helium, beyond hydrogen, and let's take a look at the entire periodic table. We have a vast array of elements that we have found, and each element in nature has a a different number of protons in the nucleus, a different number, and the matching number of electrons in its neutral form, and that is what controls uh, chemistry, and all of chemistry pretty much is encoded in the periodic table. So let's look at the periodic table and see what we can see. One of the interesting things about the periodic table, the structure of it, it has rows and columns. And all the orderly progression of chemical properties like bonding that we find in the periodic table, it's a result of the quantization of electron waves in neutral atoms of all the different sizes and all the different elements. How they combine and bond, like for instance, sodium and chlorine, yeah, those two form the salt of the earth, the stuff that we need to live. It's all because of electron staining waves. And that's because of containment. And the sweet music in this big universe is dominated by what electrons do in their contained orbits about each of the different elements. Our next lecture, our next mini lecture, will focus on bonding, sodium and chlorine, and all kinds of other bonds that we find in this universe. Thank you.